the book talks about how much energy per second is radiated away from objects because they're at a particular temperature, and that is written as an equation that looks like this. And I don't really like the letter E in this equation because we always assume that E equals 1. That just says that the amount of light that gets absorbed by an object at a particular temperature gets re-emitted 100%. So it's an efficiency number that we say when it's 100%, it's 1. And so you can kind of just ignore the E. We're not ever going to use the E. This letter here is called sigma in the Greek alphabet, and it's a constant. In all of these equations that we discover in physics, we tend to find the trend, which is that the power is proportional to the surface area of the object, and the power is proportional to the temperature raised to the 4th power, but it's not exactly equal, so we create these, what I call fudge factors. They're actually just, they're really called physical fundamental constants. But that's just a proportionality constant so that the right-hand side over here equals the power. And so we can take this equation, this value for sigma is just a number. It's actually, to me, it's a very easy one to remember because it's 5.67, so 567 times 10 raised to the negative 8. So it's 5678, but there's a negative sign you have to remember. And then because it's multiplied by area, we need to get, and we're trying to get power, we're going to have to divide by area. And because it's multiplied by temperature to the 4th, we're going to have to divide by temperature to the 4th. And we want watts because it's power, so this will be watts per meter squared per Kelvin to the 4th. And so this is called the Stefan Boltzmann Law for the people who discovered it. And we can do an example, which is going to become important later on in the textbook, that says the power that is radiated away from the Earth is because the Earth is at a particular temperature. So we know that the typical surface temperature of the Earth is about 58 degrees Fahrenheit. So we know that we cycle, the Earth is a big place. The North Pole and the South Pole stay pretty cold, but the equator stays pretty warm. And then everywhere in between goes through seasons that affect how warm or cold they are. But if you took the average surface temperature over the entire surface of the Earth, it would be about 58 Fahrenheit. And that's somewhere in the neighborhood of 13 degrees Celsius. But because of this constant here, we need to equate that to Kelvin, and you always just add the number 273 to the degrees Celsius. So it would be 273 plus 13, which is 286 Kelvin. And so because the Earth is at 286 Kelvin on average, it's radiating away energy, and it actually causes the Earth to cool. So the sun comes in, it warms the Earth. The Earth, because it's warm, then radiates back out, not as much as the sun is coming in, or otherwise we would not warm up at all. So we must radiate away less power than the sun puts in. But then there's also, we're going to learn later on, there's a balance because the atmosphere actually reflects some of the light back down onto the Earth when it tries to escape. That's the greenhouse effect. And so that also helps keep the planet warm. But the power that's radiated away from the Earth, just because it's 286 Kelvin, we can solve by solving this Stefan Boltzmann law. And again, I'm going to ignore the E. It's just sigma A T raised to the fourth. And really all I care about is how much power per area is radiated away. So I'm going to divide both sides by A. And the reason for that is I know how much sunlight comes to the Earth per square meter on the surface of the Earth, and so I'm going to make a comparison. So this will end up being watts per meter squared once I solve this. So I'll say power in watts per meter squared is equal to, oh, sorry, I didn't divide by A. That A and that A cancel, and I've divided by A on the other side because I have to do on the left side what I do on the right side. So sigma T to the fourth, that's 5.67 times 10 to the minus 8. Again, watts per meter squared Kelvin to the fourth. That's going to then be multiplied by 286 Kelvin raised to the fourth power. That means the number and the unit gets raised to the fourth power. And when I calculate that, I will get 286 to the fourth. 379 watts per meter squared.